If you have a mountain and you put some round ball on it, then this, even if it initially doesn't have any kinetic energy, this is going to roll down and it's going to have some kinetic energy, right? Where is the kinetic energy coming from?
Potential energy.
The potential energy, right? Yeah. The potential energy gives you the kinetic energy, and because of the conservation of energy, the amount of potential energy lost is going to be equal to the kinetic energy obtained. Now, there's something else that you realize that because this ball is accelerating, there is some force being created by this potential energy, right? So what's happening is that the force is given by, well, remember what's the gradient? Gradient points to the what?
Fastest increasing.
Fastest increasing direction, right? Now, would the force be pointing to the fastest increasing direction of the energy? That doesn't make sense, right? Instead, what do you think?
Straight down.
Yeah, so if I view this from above, it's like this. You have a terrain that looks like this. So these are the level curves, right? Yeah. And if you place some point here, where do you think the direction of the force would be?
Outward.
Outward, right? This is the highest point of the mountain, right? It will be going that way, right? So what's the relationship between the gradient of this potential energy and the vector of the force?
It's perpendicular.
No, it's perpendicular to the level curves, but remember where's the direction of the gradient of u? U being the potential function. This function is u. Okay? Gradient is always pointing to the fastest increasing direction, so it's going to be that way, right? So what's the relationship between the two?
Negative.
Negative of each other, right? So what you see is that force is negative of gradient of u. Okay. By the way, potential function, it's an energy. Energy is a scalar. So this function takes in two values for the coordinates of the point you're at, and it produces a single number. So it's a potential. A potential function is a scalar function. It's a multivariable function. It gives you a single value. Whereas if you take the gradient, what happens? Gradient is a vector at each location, right? So this gives you the vector field for it. So let me give you some ideas here by actually doing an example. So, sorry, this point is always a bit hard for me to explain. Mathematicians, we just ignore the minus one, and the terminology that we use is that, so definition. If a vector field is a gradient of some multivariable function u, then we call u the potential function of of U, okay, of F, sorry, of F, and F, the gradient vector field of U. Okay. So, yeah, this, for if a physicist reads this definition, they would be quite unhappy because, like, for physicists, it has to be the negative gradient. Yeah. But you know, a lot of the things that requires a minus, it's not much of a big difference when you're doing math. So this is okay. So whenever you have to translate some results from here to there, you just have to be aware of that negative sign. Okay. All right. So let's try this one. So example 1. Let UXY be, say, x squared minus 2xy. And then let's think about two vector fields. Here's 2 and negative 2. Here's C1, and this is C2. Okay, so C1 is a circular path, and C2 is a straight path. Okay. So compute. Sorry. And F is the gradient vector field of U. Okay. So compute integral C1 F dot dr and integral C2 F. Let's think about these. Solution. Well, you first have to calculate what the gradient is. So what is F? Gradient of U is, you take this and differentiate by x, you get 2x minus 2y, right? But if you differentiate by y, x squared is considered as a constant, so y differentiates to 1 and you get negative 2x. That's going to be your force field. And then for C1, we did something like this before. It's 2 cosine t, 2 sine t, where t goes from 0 to pi. So that's a parametrization, and therefore integral of C1 f dot dr can be computed as t goes from 0 to pi. F is this guy, 2x minus 2y, negative 2x. And then you divide by dt, multiply by dt, the trick that's always needed for any line integral. And then, well, what is that? That's from 0 to pi. X is 2 cosine t, right? So it's 2 times 2 cosine t, and then minus 2 times y is 2 sine t. And over here, negative 2 times 2 cosine t. So that's going to be the force field evaluated at the location, the position function RT. dotted with dr dt. So you have to differentiate this, which is negative 2 sine t, and then differentiating sine gives you cosine t, so it's 2 cosine t dt. Now do the dot product. This is 4 cosine t times negative 2 sine t, so that's negative 8 cosine t sine t. And then negative 4 sine t times negative 2 sine t, so that's going to be positive 8 sine squared of t. Is that right? Negative 4, negative, positive, okay. And then negative 4 times 2 is going to be negative 8, and cosine squared of t, 18. Okay, well, there are several ways to go about integrating this. So this part, you can integrate by setting sine t as u, and derivative of sine is cosine, so cosine t dt could be du. So you can integrate by like that. And then we've done how to integrate sine squared and cosine squared. You rewrite this as like 1 minus cosine 2t over 2, and this is cosine squared is 1 plus cosine 2t over 2. And you do that, you can do the integral. But for this specific case, it's actually easier to use the following identities, which is that sine 2t is 2 sine t cosine t. And then cosine 2t is cosine squared of t minus sine squared of t. Okay? Yeah, I'm just trying to take a shortcut here because I don't want to spend too much time. So using this, the integral becomes a lot easier. If you don't know these, then you'll have to suffer a little bit more because you have to use all these other more complicated formulas, okay? All right, so, but if we use that, then we get integral from 0 to pi of negative 4 sine 2t and minus 4 cosine 2t dt. Okay, so if we factor the 2 sine t cosine t out, then negative 4 still stays. 2 sine t cosine t is sine 2t, so that's what I get. Here, if I factor the negative 4 out, then you get, no, that's not right. This one is negative 8, sorry. So for here, if I factor the negative 8 out, then you get cosine squared minus sine squared, which is same as cosine 2t. Okay, so now the integral becomes, this becomes negative 4 over, actually positive 4 over 2 cosine 2t. And then this integrates to negative 8 over 2 sine 2t. You're plugging in pi and 0. Cosine 2 pi is, really? So you end up with a 0. Okay. All right, let me explain why later. Okay. So you get 0. Yeah, so if you plug these in, and you get 0. Now, what about C2? C2, as I explained before, you always do the terminal minus initial. So initial point, the terminal point is negative 2 comma 0, right? And initial point is 2 comma 0. So you do negative 2 comma 0 is the terminal, minus 2 comma 0 is the initial. That gives you negative 4 comma 0. That's your direction vector. And because your initial point is right here, you get x equals to 2 minus 4t, and y equals to 0 plus 0t. And t goes from 0 to 1. Now this second thing really says y is 0, right? And that's understandable because as you move from here to there, you've never left y equal to 0. You're always on the x-axis, right? And when you plug in t equals to 0, you do get 2. When you plug in t equals to 1, you get negative 2, so that also makes sense as well. All right, so how do we calculate this integral of c2 f dot dt, dr? Well, that's going to be same thing as before, 0 to 1, 2x minus 2y, negative 2x, dotted with dr dt, dt. But see, y is 0, right? X is 2 minus 4t. So that's all you get for this one when you plug in x is 2 minus 4t and y is 0. And dr dt is what? What's dr dt? This is r, right? If you differentiate this, you get negative 4, right? And if you differentiate y, you get 0. So you have to do the integral of this thing from 0 to 1. Well, times 0 doesn't do anything, so you really have to compute this one. So it's going to be negative 8 times 2 minus 4t, then you have to integrate from 0 to 1 dt, whose integral is, well, it'll be negative 8, 2t minus 4 over 2t squared. So it's like 2t minus 2t squared. You plug in 1 and 0. And then in both cases, when you plug in 1 or 0, you get 0. Okay? So you get the same answer as before. Okay. But then, there's a whole new way of thinking about this. So, solution 2. See, what is the potential energy at 2, 0? It's 2 squared minus 2 times 2 times 0, right? So that's 4. What is the potential energy at negative 2, 0? Negative 2 squared minus 2 times negative 2, which is 4 as well. Okay, so going between these 2 points, the potential energy are exactly the same. So imagine a particle moving through that force field, okay? Would it gain any kinetic energy due to the force field from here to there? The potential energy is the same, right? So there won't be any loss or gain of the energy. In other words, the work done by the gradient field from here to there would be 0 because they have the exact same potential. Okay? So this is a nice thing about potential fields, gradient fields. So here's a theorem. If F is a gradient vector field of U, some potential function U, and C is a path from point A to point B, then integral over C of f dot dr is going to be gradient of u, just u, of b minus u of a. Now this looks a lot like the fundamental theorem of calculus, right? What is the fundamental theorem of calculus? Fundamental theorem of calculus says if you have f of x dx from a to b, then it's f of b minus f of a, often written as like f of x and you plug in b and a. Yeah. But that's what that means, right? Explicitly. Yeah. And here, the derivative of f is the small f. Here, the gradient of u is this vector field. So it's like a fundamental theorem of calculus. Now, the corollary of this is that if you take two paths, they're different, but they have the same initial and final, initial and terminal, then that's just going to give you the same integral. Okay, it doesn't depend on how you connect the two. So the corollary of the theorem is that does not only depend on the endpoints if it's a gradient. Now, another way to state the same thing, if C is a loop, meaning that begin is same as end, then it's going to be 0. And that's clear from here. If A and B are the same, you're subtracting the same thing, so you're going to get 0. Okay? Well, let me try to explain in a different way. See, if C is a loop so that it starts from the same point and ends at the same point, well, pick any point here and think of C as C1, and this is like concatenation. So that's a way to say that C1 is made of first following C1 and coming back with C2. Okay, so let's say that, okay? I shouldn't be doing this, sorry. Let's say plus, okay? It's easier. So C1 and then you go to C2. But then this C1 is going to be same integral as C2 with negative, right? So because C1 connects from A to B, C1 goes from A to B. And negative C2 goes from A to B as well, because C2 itself goes from B to A, right? So negative C2, usually people write it like this, but the integral is the same thing. So negative C2 means you switch the input at the beginning and the end. So if you do that, then you do go from A to B, right? And therefore, their integral is going to be the same. In other words, integral from C1, integral of f dot dr over C1 is same thing as negative of integral of C2 of f dot dr. But then if you move this to the other side, you have integral of C1f dot dr plus integral of C2 f dot dr. And that should equal to 0 because if you move this to the other side, this side has just 0. But what does that mean? If you integrate over the entire thing, you have same number of plus and minus, they cancel each other, so therefore you get 0 if you go through a loop. Okay, so that's another way of thinking about it. Okay, and because of this, there's a second name for gradient vector field. So definition, we call a gradient vector field as a conservative vector field. So if you have a vector field that's a gradient of something, becomes a conservative vector field. Now that's like slightly wrong because of certain cases when you can have a potential that has like infinity at a point. So when you have an idealized electron at the center that has a negative infinity energy at the right at the middle. So you might have a function you may be that may have a singularity and then gets more complicated. But for our class, we'll not deal with that case. So this will be just two different ways to call the same thing.